All right, morning everyone. So tests are mostly great. We got through almost all of it on Friday. We still have one person who was an excused absence on Friday who's taking it today, so we can't just send the test back today. We will get them back on Wednesday. All right. Sorry, there's general sense of confusion on people's faces. No? Concern? Okay. Concern more than confusion? Okay. The gauge after grading it?
Like your gauge, like was it expected?
It was about expected, yeah. There's nothing. This is my 7th year teaching, I guess. 7th year, yeah. There aren't many more surprises left, I guess. So it's about as expected. Yes. No, we're only like 3/4 way through, not all the way through. So I don't have this stats on it. I'm gonna guess the class average is the high 60s. Somewhere there, based off of guess. It will be curved. Don't worry. Okay. All right. So we finished. Excuse me. Excuse me. All right. So we finished Thursday's class. Wednesday's class. We finished Wednesday's class with a very long example. So it actually took 2 whole class periods to go through. So we went through, I guess, in pretty good detail, 2 things. One, we modeled a combined mechanical and electrical system. Right? We had a DC motor, and we said this is a shunt DC motor. And it was then connected to some sort of rotational inertia. So we have a combined electrical system with a mechanical system. And then we went through the equations of motion. There ended up being 3 equations of motion with the system. We did linearization. And this was probably the first time you've seen multivariate linearization before. So we try to go through that carefully. You will have some practice on multivariate linearization in this week's homework. I know some of you have already asked me about that problem thus far, but so you're going to practice on this homework. You're going to get some practice on the second part of the project. And there'll be some examples of this in the review packet. And we'll probably throw another homework problem on that as well. And I told you this before we first went through it, but exam 2 will have a multivariate linearization problem on it. Okay? So this is not like I'm saying this so you get all scared and I'm not going to do it. It will be on there, 100% guaranteed. The only like way this doesn't happen is if I die before midterm 2 is written, and someone else writes the exam. Right? So it's going to happen. Okay. So I'm saying that because I think multivariate linearization is important. It's a pretty important skill in the field of dynamics and control. And so I want you to learn it. That's how you will be on the exam. Okay. So we went through one example. You'll have a little bit more practice as well. And we can come up with more examples if you want more practice. There's plenty of problems we can come up with. All right. So that was Wednesday's class. We finished that problem. And that was, in terms of in-depth, I'd say theory for, that's the end of it for this class, besides now using what we've learned for applications. In particular, project part 2 and 3, we'll definitely use that. The rest of this lecture, lecture 6, is not meant to go into incredible detail in terms of the function of AC type machines and also DC brushless motors, but just get some general exposure to these types of systems. All right, so you sort of understand the lingo of them. So the first one we're going to talk about today, we'll probably get through all of these today, is DC brushless motors. So what we talked about so far are brushed motors, right? These are motors with commutators, and that was I brought this in class. These are these metal contact points that contact basically contact points on the armature to then switch the direction of the electric field. DC brushless motors work in a fairly fundamentally different way. And we'll watch a video on this just to demonstrate what a DC brushless motor is. But kind of some notes on DC brushless motors. The reason why we have brushless motors is that the brushes wear out over time. So probably the most common failure mode for a brushed motor is that these brushes that make mechanical contact, so you have sliding contact between the rotating armature and these fixed brushes, which are spring-loaded, is that you have friction, and therefore they wear out over time, and then every 5 or 6 years you have to go in and replace these brushes, right, which is an expense, especially if you're talking about really large motors. And so brushless motors are a way in which you can get some of the same principles of DC motors, but without any contact with them. And we'll show a video what this looks like in a second. So just kind of notes, brushes wear out over time. So brushes are always in contact with the commutator. Causing wear. Okay, so if we look at how the commutator works, this is just a simple mechanical device. When the rotor rotates a certain number of degrees, it switches. Contactor is in contact, right? And so that's kind of built-in engineering design logic, right? So once it rotates so far, it mechanically touches a different contact, switches the electric field, and that's this nice kind of well-designed system. All right, so that requires mechanical contact, but it also works every time. So the way in which we perform the same action, right, the commutator is designed to flip the direction of electrical current. The way in which we perform this action with brushless motors, we actually use sensors and then computer logic, or just basically logic circuits, to determine and send different currents to different sections at different times. And we'll watch this video. But what is often used is will be extra elements, and so you're going to have more wires in a brushless motor. So brushless motors often use Hall effect sensors. To know the rotational position of the rotor. And electrical switches to change current direction. Okay, so brushless or brushed motors are kind of your dumb motors. They just work. They're all set up to work. Brushless motors have a little bit more intelligence to them. Okay, so they're using sensors to continually change the direction of the current from an electrical point of view. So I think that is about as much as I want to say without the help of a video. I think the video is actually going to explain this better than I can possibly do just hand waving up here. So we'll switch over and watch this. Let me get the volume here.
The recent trend has been to use brushless DC motors. They're also lighter compared to brushed motors with the same power output. The brushes in conventional DC motors wear out over the time and may cause sparking. Thus, the brushed DC motor should never be used for operations that demand long life and reliability. Let's see how a brushless DC motor works. The rotor of a PLDC motor is a permanent magnet. The stator has a coil arrangement as shown.
So just to note, they're showing this in this configuration. This is not the only configuration. They have the rotor outside of the stator, which is a little bit opposite to what we saw with DC brush motors. But this is not the only arrangement for brushless motors. You do see ones in which the rotor is inside the stator. This is just the example they're giving.
By applying DC power to the coil will energize and become an electromagnet. The operation of a PLDC is based on the simple force interaction between the permanent magnet and the electromagnet. In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized. As the rotor...
Okay, so basically, I think this makes sense from a conceptual point of view, but what's going on is the system actually has to sense the position to do this, right? You can't just say, all right, when this rotor rotates thus far, change the which coil is actually energized. You have to also know the position as well. So I forget the video gets into how this happens, but usually just like you have channels A, B, C here, you would have Hall effect sensors A, B, C. Who's heard of a Hall effect sensor before? A few people. Has anyone ever used a Hall effect sensor in one of your internships? Okay, so what would you use a Hall effect sensor for?
No, I've used them in an Arduino class.
Arduino class, okay.
Yeah.
And then, what's wrong?
I worked at like a car parts place and they used it for detecting if a car was moving backwards, like for a handbrake. So like the automatic handbrake would go off and the car started moving backwards.
Okay, so what was it sensing then? What
It was sensing which direction the wheels were turning.
Okay.
It was going forward or backwards.
Okay. And then Karsten?
For a robot, it was measuring the RPM of a flywheel.
Okay, so
For launching stuff.
okay, so a Hall effect sensor, without getting into the main details, it's a proximity. It's a non-contacting proximity sensor. So you can have basically your Hall effect sensor, and when it gets close to something metallic, the signal will change. And so in this case, like in either case, right, you can actually use it as a pretty simple odometer, and then you can say every time like a motor shaft spins, certain elements gets close to the Hall effect sensor, and that reads some sort of reading, so you know that the motor went one time around, right? And so the same idea here is they'd have 3 Hall effect sensors in the system. As the rotor rotates in a position where it gets close to the Hall effect sensor, the signal's going to go high, so the system knows that the configuration of the system is such that channel B should be actuated, right? And then when it rotates more, then it knows that channel C should be actuated. Right? So it requires, if we think of like a DC motor, 2 terminals, right? We've increased the number of terminals required to drive a brushless DC motor considerably, because now we have to have channels for the Hall effect sensor. So that's 3 channels, plus you have to have then the 3 channels for your ABC for your motor. Karsten. How's it know its position at startup? So the Hall effect sensor is always on, right? So it's going to be what signal is the strongest. Does that make sense? Sort of. Okay. So if we look at this isn't showing the Hall effect sensors in here, but you basically would you'd be monitoring Hall effect sensor A, B, and C, right? And 2 of them are going to be weak and 1 of them is going to be strong, because whatever element here is the little piece on this that interacts with the Hall effect sensor, that's going to be closest to say channel B, so channel B will be the strongest, and so you know it's in that configuration.
B, coil C is energized. After that, coil A is energized.
Okay, so just looking at this plot here, you see this kind of period, right, where this is in time. A is actuated first, B is actuated second, C is actuated last, and then also you can pulse A negative to then cause both A and C to be working together.
the opposite polarity. This process is repeated, and the rotor continues to rotate. A humorous analogy to help remember it is to think of the BLDC operation like the story of the donkey and the carrot, where the donkey tries hard to reach the carrot, but the carrot keeps moving out of reach. Even though this motor works, it has one drawback. You can notice that at any instant, only one coil is energized. The two dead coils greatly reduce the power output of the motor. Here is the trick to overcome this problem. When the rotor is in this position, along with the first coil, which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, the same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. The combined force also makes sure that a BLDC has a beautiful constant torque nature.
That's an exaggeration. You would not get a...
With this configuration, two coils need to be energized separately, but by making a small modification to the stator coil.
Yeah, so it showed this like perfect torque profile. Every single DC motor is going to have some sort of torque ripple associated. So we talked about the torque ripple in a DC brushed motor. You're going to get a torque ripple in a brushless motor as well. That was a little bit of a simplification there.
We can simplify this process. Just connect one free end of the coils together. When the power is applied between coils A and B, let's note the current flow through the coils. It's just like the separately energized state. That's how a BLDC works. But you might have some intriguing doubts in your mind. How do I know which stator coils to energize? How do I know when to energize it so that I will get a continuous rotation from the rotor? In a BLDC, we use an electronic controller for this purpose. A sensor determines the position of the rotor, and based on this information, the controller decides which coils to energize. Most often, a Hall effect sensor is used for this purpose. The BLDC design we've discussed so far is known as the outrunner type. In-runner BLDC design is also available in the market. We hope you get a nice introduction on the working of BLDC motors. Thank you.
So as you can imagine, brushless motors are often more expensive, and then the electronic controllers to control them are more expensive as well, because you have to have more information to be processing. Right? So they're not incredibly more expensive, but they are definitely are more expensive. But functionally, in terms of how they work, it's pretty similar to the permanent magnet DC brushed motors that we looked at. Okay. It's just now, instead of having commutation, which is a mechanical switch, this is more of an electrical, more intelligent switch that's happening. Okay. So functionally, they work pretty much the same. Okay. I know that was a very quick overview, but any questions about brushed or brushless DC motors before we get into some AC machines? That is really washed out. I don't know if I can change it at all. I guess I don't know what to do about it. I can't really affect. How washed out that looks. Change brightness. Let's see if that helped at all. There? That's worse? Okay. Yeah, where's contrast at on this? What? Choose a theme. Don't know what that means. I don't think this is it, right? This is something else, right? I have no idea what those are. Sorry? Yeah, which is not what we want, right? So.
Can you right click on your desktop?
Yep.
No, never mind.
Okay. Yeah, I don't. Sorry. I mean, the red is going to come. What I'm actually writing is going to come up in really high contrast. But this is probably very, very difficult for you to read. So I'll basically tell you. And then, you'll have also the notes posted online, so you can go back and carefully look at it as well. So kind of a motivation for alternating current machines. Okay, so for instance, most alternating current machines don't use single-phase AC like we have in this room. They use three-phase AC. We'll talk about three-phase AC in a second, but I don't know if you've ever taken an oscilloscope and measured what's actually coming from the wall, maybe some of your intro to engineering classes, but we have alternating current running through our entire world here, right, in terms of electricity. And so if we ever wanted to power a DC motor, we'd actually have to rectify that current to give us a DC power signal. And so then I think a natural question is, why don't we just use the power as is that's pumped through all of our buildings, right, especially industrial spaces as well. So infrastructure power. Is AC. Why not use as is? Okay, so DC power requires rectifying the AC signal. Okay, so that's one motivation for this. We'll talk about some other motivations after we go through the function of this in terms of how AC power can be used very effectively for speed control. But just to note, if you ever wondered kind of what your signal looks like coming from your wall, it's basically V. That's maybe where it's hard to read. I'll just write it down here. V is equal to A cosine omega C T, where A is equal to 110 volts. Omega C would be equal to 2 pi times 60, which is then 60 hertz. Okay, so if you go to Europe or anywhere else in the world, this would be 50 hertz. I forget, there are a few other countries that are 60 hertz, but not many. Most are 50 hertz. Across the world, they're usually 210. But in the United States, we have 110 and 60 hertz signals in our walls. It's not so much a problem anymore, but a decade ago, it'd be very common for someone to go to Europe and like basically blow their hair dryer or some other tools that they brought with them because they were using basically the proper equipment in between the line in Europe or elsewhere in Asia and what we have in the United States. They just try and plug in some sort of appliance made for a U.S. power system, and you blow it really quickly. The power supplies now are so much better. So if you ever read the back of this, you can see that your input now can be, let's see, where is it at? Yeah, so this says the input can be anywhere from 110 volts to 240 volts, and anywhere between 50 and 60 hertz, right? So now anymore, pretty much a lot of electronics can accommodate both. This wasn't the case, say, 15 years ago, something like that. You'd pretty often fry your equipment on accident, right? But now, hey, everything's better these days, right? So, but anyhow, just to know, that's what's at the wall here. It's slightly different if you go to Europe, Asia, etc. If we look at what we talk about three-phase AC power, those of you who have had internships at manufacturing plants or other places like that, you may have had to look at spec sheets for electrical system, or maybe you had to install something where you had to have three-phase power. I don't know if anyone had that experience in one of your internships, three-phase. Okay. So there are quite a few labs in this building that requires three-phase power. And then pretty much anywhere that has a manufacturing facility, they have the regular 110 single-phase throughout, right, to power laptops and computers and all these other, I would say, low-power devices. But then all their really heavy-duty machines will often have three-phase power on them, precisely to drive AC motors is the main reason here. We'll talk about that right now, actually. So if we look at what three-phase power is, if this was our single phase, right here, just single voltage, single cosine wave, three-phase power is we'd have now three signals through our circuit. Say we'd have VA, which had amplitude A, cosine omega CT. Okay, this is still be at omega C 2 pi times 60, so it's 60 hertz in general. The A here is very variable. This is oftentimes tuned to the exact piece of equipment you're trying to drive. So this is going to change considerably. So we'd have the signal A would look just like our single phase power system. And then VB would have a phase shift associated with it. Okay, so 2 pi over 3, that's a 120-degree phase shift. And then VC would have a phase shift as well. All right, so I'll fill in the middle in a second. But if we would look at the current going through the system, so this is time. This is saying what the voltage is. The current is going to be dependent on what the impedance of that system is at a certain point in time. So we'll just make this go from I bar to negative I bar. And then we break these up into different sections. So this would be pi over omega c, or 360 degrees. Pi over omega c, this is 180 degrees. Okay, so we'll draw this out Okay, so if we look at VA, or the current coming from A, right? So this is going to be, if it's a cosine wave, this is going to be a value of 1 at 0 time, right? And then it's going to be -1 at 1/2 period. All right, so this wave is going to look like cosine wave. All right. All right, so VB. If we look at VB, if this is phase shifted by -2 pi over 3, this is going to be its highest, or a value of 1, at 2 pi over 3 in terms of that part of the period, right? So this is where it will then be the lowest somewhere in between. That's a little more complicated to specify. But then it would have this basic shape, so it's going to be shifted. Okay, so I forgot to label this. This would be IB. IA. And then the last one. Okay, so IC is advanced by 2 pi over 3, or you can think of that as being, advanced by 120 degrees, or you can think of this as being delayed by 240 degrees, however you want to best think of this. So it's going to have its highest point at 4 pi over 3 omega c. And have this basic shape. And then this one did not go down far enough, so let me redraw that. Okay. So we have this basic shape. So we have 3 phases going into this system. From electrical schematic point of view, we have 3 coils. And we have then 3 voltage that are going to be specified. So we have VA, we have VB, and then we have VC. And I'm showing this in terms of a triangle. This is basically how the thing is wired up, is that not only are the electrical phases oriented 120 degrees from them, but often the geometry of these coils are oriented 120 degrees from each other as well. Okay, so then we have a common connection point between them, and then these 3 coils. Okay, so this type of configuration. Okay, so then how this looks in terms of the stator is we're used to seeing a stator, which is, especially if it's an electromagnetic stator, we have just a single, basically just 2 different sides to it. This is going to be a little more complicated here. So here's our stator. Okay, if it's just a single phase motor, which we saw before, we would simply have, say, current going into the page on this side, and current going, current going out of the page on this top side, current going into the page on the bottom side. So this, for instance, in this configuration here, this would be so I matter, but let's say it would be A and A prime. So this would be the A side, and then this would be the other side of the coil, A prime coming out. But since we have a three-phase motor system, we have a little more complicated of an arrangement here. And so we would have B primed, C primed. And this is important to note that this is just at an instant in time. Okay, so because these are alternating current signals going from the highest level to the lowest level, the direction of the current is going to be continually changing. It's going to be flipping at a rate of 60 times a second, right, if it's a 60 hertz signal. Right, so this is just one little snapshot of time. And we'll walk through the snapshots in just a second. But before I get into that, any just kind of general questions about the structure, the idea of three-phase power here?
Are we going to talk about like the delta configuration too?
What do you mean by the delta configuration?
Well, I've seen it like that's like Y, where they come in.
Okay.
And then I've seen them where it looks like a triangle, and the coil's like a triangle.
Okay. So this is not something I'm aware of then.
Okay.
So, no. This is based largely on the book, and this is the it's taught there. It's only this one. Yes.
Like, at the state of time that the ones going are out of the page and into the page are opposite of each other?
Yes. Yeah. Yeah. Well, we'll get to that in a second. Yeah. We'll walk through why that's the case and why that's advantageous. Okay. All right. So this is the general schematic. Let's look at. Let's look at a few different snapshots here. Okay. So we'll start off with, I'll just rewrite this so everyone can see this really well. T is equal to T1. All right, so this will be our first snapshot in time that we're looking at here. And I'm going to heavily leverage the schematic here. So this would be what we'll define as T1. Okay. So just to note, this is just my hand drawing. It's not the best hand drawing in the world, but if these time ones should correspond to this intersection point here and then this line intersecting the lowest point on channel IC. Okay. So sorry for my poor drawing, but that's the intention here. So if we look at this configuration in time, drawing our stator here. So keep in mind these are currents that we're representing here, not voltages. But in this currents, in the current here, I'm not every single one here. This is going to have exactly the same configuration in terms of labels. This is A primed, B, C primed, and then C. And so we look at all these. If you look at signal A is the green line here. Current is positive, right? So that means that current is going into the page at A, and it's going out of the page at A primed. Right. So if we look at this case, right? If I use my thumb as current going to the page at the very top, it's not tall enough, but the top current going into the page, wrapping around, flux is going this direction, right? And then at the bottom of the page, current's coming towards you all, so the flux is still going in this direction, right? So I have a small contribution of flux from phi A, and I'm saying small because relative to the current in channel C, right? Channel C is at this very peak low in terms of current, and then A is somewhere in between, right? So if I look at the flux contribution here, I have a small segment going in this direction. And I'll call this VA. Let me make this a little darker here. All right, so same idea with B. All right, at B, it's a positive current, right? Based off this chart, this is the blue line. So I'm going to have flux going into here. Same argument, but these are rotated 120 degrees from each other. B is same strength as A, so it's going to be a small line segment going in this direction. All right, and then if I look at C, C is negative, right? So here here's the positive convention for C. This is current going from terminal C to C primed, but C is negative at this point in time, so it's actually going the opposite direction. So it's going, in this case, at us. Let's see, sorry. It's going into the page at C primed, and it's going out of the page at C. So same idea here. Then we're going to have a very large flux. So I'm drawing this as a longer arrow in this direction here. All right, so if I then look at what is the resultant flux, so I have resultant flux coming from, you can look at x and y components of all of these flux terms here. Okay, so, or you can look at it, how well it aligns with phi C. You see some of these, in terms of phi A and phi B, are going to cancel out. But in large, it's going to then add to this flux. So we have a total flux in this direction here at this exact point in time, right? So even a millisecond later, this configuration is going to change, right? All right, any questions on that general idea? And we'll look at how this rotates in a second. All right, time is equal to 2, or T2. Okay, so T2, if we look at the case of T2, all right, so our labeling of terminals doesn't change. The structure itself is fixed. So every time, this is going to be A, this is going to be A primed, B, B primed, and then C primed, C. All right, so if we look at time 2, A and C are going to change in terms of their direction, right? So at time 1, A was positive. Go fast forward to time 2, A is negative. So whereas in the previous time instant, A was into the page, it's now going to be out of the page, and vice versa for A primed. Right? So this, it's also at its strongest point too, as well, right? So before here, it was not quite the full amplitude. Here it's the full amplitude. So the flux here from phi A is going to be large, and it's going to be in this direction. B, in terms of sign, stays the same. Right? Before B was positive, it's still positive in this time point. Okay, so nothing has changed there. Okay, but C has changed sign. So at time 1, C was negative. Now it's positive. So these flip signs. BC. Okay, and so now if we look at the resultant flux from this configuration, this is the resultant flux. Okay, so if we note what's happened here, this is time 1. We have whatever that is. If we look at this from the positive right angle, this is probably a phase. This is probably a phase angle of around, I'll say somewhere on I don't know, what is it? Probably 110 degrees or something like that. It's 120. Now it's at 0 degrees. So we've had a rotation. Has rotated clockwise, right, in time. So this flux, we now have a rotating stator field, right? Before, with all DC machines, we had a constant stator field. Now we have a rotating stator field. Just to complete this entire discussion here, we'll talk about the very last time step of interest. This is going to be time 3. Okay, so time 3. We're going to have A positive again. So that's going to be the original configuration. B, if we follow B here, B is going to be negative, and it's actually going to be its strongest. So that flips based off the in comparison to the previous time points. So this is going to be now in this direction. And then C is going to be positive. So for now, a total flux in this direction again. So flux again rotated clockwise. Okay, so as time goes around, this in terms of this flux, we just continue to go in a clockwise rotation as we keep on going with time with more periods.
As the name suggests, synchronous motors are capable of running at constant speed irrespective of the load acting on them. They are machines with high efficiency and are mainly used in high precision applications. The constant speed characteristic is achieved by interaction between a constant and rotating magnetic field. Rotor of synchronous motor produces constant magnetic field, and stator produces revolving magnetic field.
All right, so we didn't go through this, but the rotor in this case would have to be a DC electromagnet, right? So this is going to be constant in terms of, if we look at coordinates that are centered on the rotor, so that therefore the coordinates rotate with the rotor, be constant in terms of its magnetic field. The stator is the one that's not constant in terms of its direction.
The field coil of stator is excited by a three-phase AC supply. This will produce a revolving magnetic field, which rotates at synchronous speed. Rotor is excited by a DC power supply, so it acts like a permanent magnet. Alternatively, rotor can also be made of permanent magnet. Interaction of rotor and RMF is interesting.
Okay, so just to note,
Assume you are giving
so
an initial
what we talked about here, we had just three basic phases, and then they only had one pole associated with each. This is the case of a multi-pole motor. We'll talk about that in a second. But you can see as this is rotate, this is the stator field. It's rotating in time.
You can see that opposite poles of RMF and rotor will attract each other, and they will get locked magnetically. This means that rotor will rotate the same speed of RMF, or rotor will rotate at synchronous speed. Synchronous speed can easily be derived as follows. This means that if one has not control over frequency of the electricity, speed of synchronous motor can be very accurately controlled. But if the rotor has got no initial rotation, situation is quite different. North pole of the rotor will obviously get attracted by south pole of RMF and will start to move in the same direction. But since the rotor has got some inertia, this starting speed will be very low. By this time, south pole of RMF will be replaced by north pole, so it will give repulsive force. As a net effect, rotor won't be able to start, or synchronous motors are not inherently self-starting.
Okay, so this is getting a little bit into the minute details of this. Okay, yes?
So does, like, the DC power to the rotor, does it have brushes?
So if you'd have to have some sort of, not necessarily brushes, when I think of brushes, I think of commutation, right? So that you're continually switching, but you have to have some sort of slip ring type system to continually rotate. I don't know if you've ever seen slip rings before. Okay. Okay, so a slip ring, it's more of a mechanical design type topic, but this is if you imagine you have a contact that's now circular, and then you have a point that's always touching. That's a way in which you can transmit basically electrical signal around something that's rotating. If it's wired, eventually you're going to get to it just keeps on winding up, and you're going to rip your wires apart, right? So definitely either have a slip ring, or also you can have permanent magnets in the rotor as well. Those would be your two options. Yes.
What are the advantages of having a permanent magnet instead of DC?
So one is you're not going to have wear associated with the slip ring. Other advantages, they're usually stronger and lighter in terms of stronger for the size that you have. But we talked about some disadvantages about you can demagnetize it on accident if you have excess temperatures, excess magnetic fields, etc. But you get a lot of really expensive systems, motor systems, they're permanent magnet systems because you get more power per size. I'll show an example of one, probably not till Wednesday because we only have 1 minute left. I wanted to, in this very last minute, I wanted to talk about this idea of this synchronous speed. Okay, so if we are using basically some sort of signal that's coming from infrastructure, the wall, it's pretty tightly regulated to be 60 hertz. Okay, it does fluctuate, but in general, it's actually pretty close to 60 hertz. And so what this allows you to do actually is drive a motor system at a constant speed quite easily. So this is called synchronous AC motor for a reason, is that if you have three-phase power, each of those phases are at 60 hertz, you can then get a motor speed that is some, and we'll get into this in more detail in Wednesday's class, that is some proportion of that frequency. So in the US, this would be 2 times 60 seconds over, never mind, that's not what I was looking at. This frequency would be, in this case, 60 hertz. Okay, so that means if we want to do some sort of constant speed operation with a DC motor, we have to have a lot of control systems in that to pull it off, in which we'll talk about the whole rest of this class about control systems. What's nice about synchronous motors is that as long as you don't try and drive a load that's beyond what they're capable of, they will run at that speed. So if you need some sort of constant speed system, you can just buy the correct AC synchronous motor to pull that off. So what I mean by that, so if you look at a spec sheet, so here's Baldor, which is these are used everywhere. This is a very common industrial motor that you could potentially purchase. And if you look at spec sheets for this, they have different horsepower motors that you can buy, 3-phase, and then also you have different speeds, which you buy this motor. It determines the number of poles in the motor. So that's the number of basically a number of A prime, B prime, C prime poles in this motor, and it will run at, say, either 360 RPMs, 3600 RPMs, 1800 RPMs, 1200 RPMs, 900 RPMs, and it will always run at that speed. Okay, which is very helpful because in a very simple system, you get a system to run at constant speed for you. That, I'm out of time. We'll reconvene on the subject on Wednesday's class.